Hello, my name is Ian Watson, and I am the Executive Director of the American Membrane Technology Association. The interview you're about to see is one of a series in what we call Chats with the Pioneers. AMTA is a technical association founded on the advocacy of the use of membrane technology for water treatment, from wastewater reclamation and reuse to seawater desalination. The heart of this technology is the membrane itself. About 2.5 years ago, our board of directors decided that to preserve the history of the membrane and membrane system development, the association should make an effort to record these chats with those responsible for launching what is now a technology in common use throughout the world. AMTA's intent is to make these segments available on its website so that a new generation of engineers and scientists can understand the efforts of those pioneers who helped solve some of the problems of the water issues facing the world today. Today we have 4 gentlemen from the DuPont company, all of whom were involved in the development and application of the Permacept separator, the Permacept membranes. On my far right, Dr. Lynn Applegate. Next to him is Jack Strantz, Tom Eckmann, and Charlie Brown. Perhaps, Lynn, you'd like to start by telling us a little bit about yourself and your background and your time in the Permacept division of DuPont.
Okay. I got my BS degree in chemistry in 1963 from the University of Dayton, and my PhD from Indiana University in 1967. I then came to work for DuPont in the R&D division of Permacept, and I worked in that division for about 5 years, working on various problems involving our water membranes, aromatic polyamides. After about 5 years, I transferred to the technical service section and spent the remainder of my career in technical service, working on various problems. The early days of Permacept found that most people did not understand reverse osmosis, how to build systems, and how to encounter or what pre-treatment or post-treatment was required for water systems. And so a lot of the efforts in the initial stage was to try to educate engineers, consulting engineers, and water companies about reverse osmosis, where it could be applied and where it should not be applied.
Thank you, Lynn. Jack, how about you?
I graduated from the Drexel University with a degree in mechanical engineering in 1965. I worked for the DuPont company at that point, and I was in the engineering department in the research division. My first assignment with Permacept, with DuPont, was to work for Permacept. At that point, they made gas permeators, trying to recover helium from natural gas. And I came in and to finish up a project, mechanical project of a hank winding machine to make the hanks for the Permacept permeators. My job also involved helping Permacept cut open these permeators. At that time, these the gas permeators were approximately a 12-inch diameter pipe. They were about 10 foot long. The hank was put into the pipe. The 2 ends were capped. The device was then put into a centrifuge, and epoxy was put on both ends to make a head and seal the unit. After the head was made, the epoxy was made, then the epoxy was cut with a saw, and then an individual would sit down with a scalpel and actually cut open the fibers to open up the hollow fibers. At the place where I worked, the Engineering Development Laboratory, in the engineering department, one of our people there developed a technique to open up these fibers with a lathe. And I was working on that project then, finishing it up to help get this done. And I would coordinate work with the OrChem department who made the permeators to get these devices shipped over to EDL open up the fibers and the permeators, and then send them back to the OrChem department for their further testing. Then I continued, this lasted about 1 year. Then I began to work on other programs in the DuPont company. I spent about 5 years on the PET bottle program, the 2-liter bottles that are out there now. And then eventually DuPont decided that wasn't a business for DuPont to be in, unfortunately. And I was transferred to an operating department at that point. Then from that operating department, I went to Perma-Sep in 1976. And I worked there in the technical services division, working on problems with customers, training people, helping to write the DuPont Technical Information Manual, working on the computer program to predict performance of our permeators in various operating conditions and that sort of thing. This work then eventually led me into a split off of Perma-Sep called Separation Systems, where we worked on, tried to expand, going from water recovery systems to industrial waste and fluid streams, and in addition to concentrating of fruit juices. I spent about 5 or 6 years in that program, and then again DuPont terminated that program, and I went back to Perma-Sep and spent the last 10 years of my career with DuPont in the Perma-Sep.
So you were with a couple of programs that got terminated.
Unfortunately, yes, not just a couple, a lot of programs. DuPont does like to terminate programs.
Thanks, Jack. Tom, how about you?
I started at Washington Works in Teflon, so I've made Teflon, and then I also moved to CNP and put color in Lucite. I was the maintenance supervisor over Teflon, and then I got transferred to Sabine River Works, where I ran the central shops and had like 100 mechanics under me. But I decided I didn't want to get into supervision, so I moved back into the technical group and went and worked in the powerhouse at Sabine River Works, which was the biggest energy user in DuPont. We used more energy than the city of Houston used in one day. But then I got lucky and I got transferred to Perma-Sep in 1978. And I can say my career in Perma-Sep I was the luckiest guy because I think I had the best job in the world. We were working on a product that was doing good for the country. We were making water out of seawater. We were going into countries, and every day I would get up and come into work. And Jack and I were in the same carpool, and I got involved with pressure vessel development, and then we made flat membranes, which really wasn't too successful, and we learned a lot, and we'll tell you some stories about that later. But later on, I picked up a lot of the work that Charlie had in press about modeling the fiber. And there was a general manager that said we should be empowered. And I kind of like self-empowered myself to kind of like come up with some developments. So I modeled how the fiber worked, and I came up with some ideas of how to put 2 bundles in a vessel, and then later on we learned how to double end the fibers and take the water out both ends, and which made the fiber a lot more productive and got a lot better salt passage. And we actually came up with a cartridge device that worked like a spiral, where you could put multiple bundles into a vessel. And my only regret is if we would have done that with the B9, I think back in 1980, when we first were working on B9, I think we would have really done well in the brackish business, because we learned that we could run B9 at like 200 pounds pressure and make good salt, especially if we applied the post-treatments. But every day I would get up to work, and I enjoyed going into work. So in DuPont, that's pretty rare, because we were a small, self-contained business where we had marketing, technical, who ran the plant, and manufacturing all in one place, and we were like one big happy family. And in DuPont, where you have these big chemical plants and you got marketing guys that work in Wilmington, that was a rarity to have everybody all in one position. So it was an honor to work with all these guys, and you look back at some of the technical achievements we've made. Charlie came up with CBX epoxy, which we couldn't have had a product that could operate at high pressure without that epoxy. Lynn came up with ways to improve the post-treatments and ways to kill the bacteria. Guys like Jack would help figure out how to operate the plant successfully, and we kind of took that business from the early infancy to the end where we could make seawater at a very small price and build large plants and have them work. Like in Malta, we started in 81 or 82, and we had some little problems with pressure vessels, but we worked through that. And then we had a biofouling, we worked through that. And the membranes in Malta were running when they decided to get out of the business, which was like 20 some years later, with the same original membranes, which to me was like incredible. So I'll pass it on to Charlie.
Thanks, Tom. Charlie?
Yeah, okay. My name is Dr. Charles Brown. I received my bachelor's degree in chemistry from Mississippi College in 1954, a PhD in physical chemistry from the University of Texas in 1959. I did a one-year postdoctoral stint at the university. Then I joined DuPont in the film department in 1960. I was transferred to Orchem on the working on the Permacept products in 1964, maybe 65. It was around the end of 1964. The first product we worked on was a hollow fiber Dacron system for separating helium from natural gas, and the program rapidly developed into trying to develop membranes for desalination of brackish water and eventually seawater. Our very first membranes were hollow fiber. Our first desalination membranes were hollow fiber 6/6 nylon, which had went through a series of post-treatment processes after the fiber was developed. And I had the fortune to share a lab with a guy named John Richter, an organic chemist who was one of the first developers of the aromatic polyamide membranes, and actually also some of the polyamide membranes, which had much better salt rejection and just generally better desalination properties than the 6/6 nylon. I continued to work in that area, both on improving the mechanical properties of these membranes and also working on epoxy systems which we needed to seal the membranes and so that they could operate under higher pressures. And I stayed with Permacept until it was about 1975 actually, and Permacept got transferred, the Permacept group got transferred from the Organic Chemicals Division to the, went through various names, but it was a Polymer Products Department, was probably the most common name. It changed names periodically. And when that occurred, they transferred a lot of us back into Orchem. I worked for a couple of years in the dyes division in Orchem, and then Permacept decided it needed to expand its technical group again, and they transferred some of us from or came back to polymer products and worked on that, both on the aromatic polyamide membranes, primarily trying to improve the salt rejection and the flux and the mechanical properties by a series of post-manufacturing steps, including annealing the fibers with special solvents, a lot of that stuff, and also to develop epoxy systems which would operate at higher and higher pressures without undergoing significant creep and eventually destruction of the device, and stayed there until sometime in the late 1980s, late 1980s, and then was transferred back to a gas separation program, which was used aromatic polyamide membranes, and worked there until I actually retired from the DuPont company in 1992, I think. So that's pretty much it.
Yeah, it's so the total history of the Permaset group from its inception to the day they closed the doors was how long?
Probably somewhere around 1963 or 64 in the beginning, closed its door in 2004.
So it's 40 years.
40 years.
Yeah, I didn't remember exactly when it shut down.
It was 2004.
I started in early '64.
It took a long time for them to shut down the Permaset business because people wanted the product so much.
That's right. Well,
I left in July of 2004. When I came to work that day and my computer was turned off, I decided there's no longer any need for them to have me as a consultant, so I left. And that was it. They were basically shut down at that point.
Yeah, but by 2004, there were a lot of Permaset plants around the world.
Yeah. Well, what happened was we notified people probably around 2000, somewhere in that range, maybe even a little earlier, that we were going to go through a shutdown. And we gave them several years to find alternative manufacturers or to buy membranes from us. And so then I actually retired full-time in June of 2002, but I was asked to continue to work as a consultant until they went through all the membrane and had all the all the other conditions completed. And so that was about July of 2004.
Yeah, I was at a conference, must have been around 2002 or 2003, and there were some people there that were trying to gather up some interest in actually licensing the technology from DuPont and continuing to make permeators.
That's true. Yes, we had several people. In fact, Coke was one of the people that came and looked at us. There was a number of people that took a look at us, but they decided they did not want to purchase the technology.
Well, the problem was the fiber was being made in the middle of the Waynesboro plant.
Yeah.
And DuPont wanted to sell the Waynesboro plant to get out of the nylon business. So we were basically shut down because DuPont wanted to sell the nylon business. We had the best seawater membrane at that time. In fact, we were in negotiations with IDE and we had won the bid to use the seawater hollow fiber cartridge. And the fellow from IDE was actually in our plant testing. Boris Lieberman, I think his name was testing the triple cartridge at the time we went out to San Diego for IDE, I think it was. And we all knew what DuPont's intent was, but we needed to continue going through the exercise because DuPont did not want a long-term commitment for that plant, which I think was like 14 years, something like that, because they knew they wanted to get out of that business. So that was the unfortunate part about being in Permaset is we'd gotten the business to the point where We knew how to treat, get rid of biofouling, and we knew how to use the fiber really efficiently. And we had devices that were economical with, they could produce a lot of water with less piping and fittings. Being a small cog in a big business, we didn't have any leverage. So that's why Jack stayed and I moved on and other people moved on. But
Let's go back to the beginning. You were working in the hollow fiber was developed initially for gas separation, is that correct?
Gas separation. It was a so-called barrier one hollow fiber membrane, which was basically a Dacron hollow fiber. And the units were mammoth compared to the seawater membranes. I mean, we had to use extremely heavy moving equipment. These things were what, 10 or 12 feet long and 12, 14 inches in diameter, steel shells. And
they actually had pits in the Permacept building where they spun them, right?
Well, the original pits were over at Orchem Department, Jackson Lab, over at Chambers Works. That's where they manufactured them
Right,
first.
I think they
Then they
also did
designed
the
Permacept,
Permacept
and they designed the Permacept building with the centrifuge pits in there. But then after the building was designed and construction was underway, they changed the method of manufacture and they changed the whole process in which the device was made, and they eliminated the pits and filled them in.
How was the change in direction made to go from gas separation to desalination using a similar configuration of hollow fiber?
that was almost from the beginning. I think people realized very quickly that the gas separation market, or at least the helium separation market, was never going to be that large. And they said, we had the technology, spinning technology, why don't we look for other uses for this concept of hollow fiber separations? And so as almost within a year or so after it was started, we were started spinning nylon 6/6 hollow fibers. This was all done at the Kinston Textile Fibers plant. And but again, very low water flux rate, so there was a lot of initial work done on on post-treating these fibers, these nylon fibers, to improve the flux characteristics while still maintaining reasonable rejection. But basically the aliphatic polyamides like nylon 6/6 just didn't have either the mechanical strength or the separation properties to be a marketable system. And so people were working very early on looking for new polymer systems that we could use that had both better mechanical properties and separation properties, salt rejection properties. And people like John Richter and Harvey Hain worked on that. There was a well-known patent, the Richter-Hain patent, for aromatic polyamides, and I believe it also covered just about everything that had an aromatic group in it. And that was looked like it was the way to go, and we proceeded in that area. And there was a lot of work done on, even with those membranes, and improving the salt rejection. And getting the flux up. As I say, we worked for years and years improving that continually. And we had all of these post-treatment systems, both in the final stage of the spinning process and also in after the units were fabricated, after the fibers were fabricated into devices. There were again additional post-treatments and so on, everything to get the salt rejection up and improve the mechanical stability. These fibers all under high pressure creep and they become more compact and you get the flux decline, and so you had to try and overcome that to the best of our ability. And not only the fibers but the sealing devices, the tube sheets, we had to develop epoxy systems which would hold up under these high pressures without deforming over time and eventually losing the ability to seal the systems in the...
Do you know what happens with tube sheet creep? Okay.
Yeah.
The O-ring, the groove actually gets smaller in diameter, so you lose the squeeze on the O-rings and then you get
the O-rings
bypassing.
In those days, OSW was just getting interested in membranes, and they had a fairly aggressive gentleman there, Dr. Chanapasapa, who was pushing membranes. Did DuPont, the Permaceps group, deal much with OSW in those days?
They had a research facility at Ocean City, I think it was Ocean City.
There was some work.
So they had people assigned down there, and they were testing membranes, seawater membranes at that point. That was, I guess, in the early 70s. One thing, I think that the current membrane or current device shape that we wound up with the B9 and B10 membranes, I think a man by the name of Steve Cope from the engineering department came up with that concept of making a membrane, getting it away from the centrifuges and the double-ended bundles that they used to use in the early days.
Was the first permeator called the B1?
That was the very first permeator, was a B1 gas separation permeator designed for helium separation from natural gas. And then I'm trying to remember what were I don't remember what we called the nylon hollow fiber units for our first attempts at desalination.
I think that was called B5.
That's
B5
what I was
is what I
thinking.
remember.
And that was a steel pressure vessel, wasn't it? B5,
Yes.
as I recall.
They probably all were in those
Yeah,
early days.
yeah.
They were
'Cause I
stainless
used to
steel
have-
pipes.
I used to have a slide of a DuPont
I have a picture of one.
permeator
Yeah.
on the side of a condominium building
Okay.
in Florida. And it seems to me somebody told me that was called a B5.
Yeah, the B5 was, that's correct, it is. And then the B9s were the brackish.
So you skip 6,
Systems.
7, and 8? It's kind of like the fifth,
That I don't
third
know.
bank.
Yeah.
I
Without the others.
don't know, we had some units in there. We were working at various times on trying to develop, to a limited extent, trying to develop some spiral wound film systems and
Yeah, well, that came later, though.
I think there was a 6, 7, and 8, but
Yeah.
they weren't commercialized.
yeah, they may have been some of the early polyimide work and so on.
And,
So I
and the
started
B-
in the industry in 72 or thereabouts, and I only remember the B9 as being the first one.
Well, they were the only ones commercialized.
Yeah.
From B9 was the first
B9
one.
was the first aromatic polyamide hollow fibers.
And what sort of characteristics do those fibers have in terms of flux and salt rejection?
That was
Well,
just the brackish water systems. They operated at 400 psi.
They had like
It all depended on
17% salt passage before we added our PTB,
PTA.
our PTA, and
PTA.
then it would come down to like, what, 7 or 8%?
10, yeah, it would be under 10.
Under 10.
The idea was just to try and get a product that had less than 500 parts per million dissolved salts in the product operating at 400 psi.
See, at those time, we made the flow rate depend on the size of the unit. We made 4-inch devices first, and then they made 8-inch devices. Then we eventually got to 10-inch devices.
Yeah.
And so each side had a...
There were a lot of plants in Florida in the early days, most of them built by Permuted or Polymetrics.
Right.
Yeah.
And it seems to me they all were around 93% salt rejection or something like that.
Yeah.
Well, a lot of it depends on, that's on a sodium chloride basis.
Yeah, right.
So it all depends on the salt, you know, the
But you had the same
contents of the water.
characteristics as the flat sheet membranes. You got better rejection of the divalent ions.
Right, absolutely.
The
4%.
B5 rejected the divalent ions pretty good,
Yeah.
but not sodium chloride. But the B9 really was a vast improvement in rejecting the sodium chloride ions.
Now, when you went from the B9 to the B10, in addition to PTA, you used to use PTB as well.
Right.
Yes.
And
we could also-
that gave you enhanced
And
rejection.
Well, we could put the
also-
PTB
we
on the
also
B9
use-
as well, and that would improve the, you know, basically cut the rejection in half.
Right.
But then you lost a little bit of flow.
We also used on the seawater units, that was buried at B10. The polymer composition was slightly different, so we had a combination of better salt rejection, but at some expense, the flux was lower on the seawater units at a given pressure, but
Also on a B10, the diameter of the fiber is slightly smaller than the B9 fiber.
Yeah, but it's
Yeah.
just so we can record
Yeah,
it for history. What was the fiber diameter inside and
Approximately the
outside?
size of a hair,
the fiber diameters were about
90 micron.
if you want in microns, the B9 and B10 were both in the OD of the fiber was about in the 80s microns, and the ID was roughly in the upper 30s, 40 to 40. The diameter of the B9s was slightly, inside diameter was slightly greater. We just didn't need it, since they operated at lower pressures, we didn't need as much the mechanical strength that we needed for the B10s.
There used to be, you probably recall the late Richard Arlen Smith and his newsletter. I can remember, I was just a young guy in those days, but I can remember heated debates that took place in the Water Desalination Reporter about the benefits of hollow fine fiber versus flat sheet spiral wound membrane.
We always thought he didn't like us.
Did he actually call up and needle you about that, or?
He didn't call me, but there were comments between our management and him, yes.
Yes, I'm sure there were. As the spiral developed, you were, I would assume, watching its development closely. And at some point, did it appear to the Permaceps folks that this was a sincere challenge to you? Because you had a pretty dominant market position in the late 60s, early 70s.
I think the Yuma project was where things really came to a head in that project, because there was a lot of research done at Yuma between Hydronautics, UOP, and DuPont. And I guess we felt like our membrane performed the best, that we had the original membranes in there from day one and they stayed in the whole time. Whereas UOP and Hydronautics continually changed out their membranes. Then when the bid came, DuPont was left out not on the bids, but on accepting of the bids. We were totally left out. I think Hydronautics got one of them got 20%, the other got 80% of the business, and DuPont got nothing. And all the technical work basically came out to be a wash. In other words, they didn't really evaluate. It all got down to economics. And so at that point, I think there was a big change in the way people perceive things.
And there was that decision, I believe, precipitated a fairly lengthy litigation
It did.
And by the time it was finished, the CA membrane was pretty much given ground to the TFC membrane.
Right. Yeah, Film Tech basically, I think, from what I understand, Film Tech took the Richter and Haynes patent, the composition in there, and basically came up with a thin film using that very similar polymer with slight changes that got around the patent.
Then ultimately, Permacept did move into the spiral market with,
Well,
I remember the A15.
Dow had the CA hollow fiber membrane.
Yeah, Dow had the CA
And,
fiber, right.
They were having troubles with that. In fact, they had the Sarasota plant in Florida, and they had a retrofit of that plant, and the retrofit was with DuPont membranes. And I think we had a very aggressive marketing manager that in those days, and he was extremely good. Jack Sally.
Oh, yeah.
He was a really great man. And so I think then what happened was Dow actually bought Film Tech.
Yeah.
And they converted to spirals. And at that point, then we began to look at spirals with things like B15 and some other membranes, A10.
We didn't do a very good job on spirals.
Why was that, do you think? I mean, you certainly had the chemistry.
We tried to invent everything ourselves. We came up with the B15 membrane based on the polyaramid. It's highly sulfonated. And there were a number of things. We coated it up in Towanda, and the guy who was the research guy wanted to be successful. And when he tested the membrane, he took out all the, he had a cation exchange unit, and he ended up taking out all the magnesium and calcium to get his results. So he got good salt rejection. But yet, when you put it in the field, all of a sudden, what we got in our cell tests didn't correspond to what we got when we put it in the field when the calcium magnesium was present. The other thing is, because it was sulfonated, the membrane compacted, and so when you rolled it up like in a jelly roll in a spiral, now all of a sudden what was a membrane that was 7 mils thick or whatever, I can't remember the numbers, now became like 5 mils thick. So now all of a sudden you got this slop in a spiral cartridge. And the cartridge wouldn't work very well. And then we decided, well, we'd do a thin film composite like Film Tech, but we didn't want to infringe on their chemistry, so we came up with our own A15. And we eventually put the unit in at Glasgow, and we improved it, and we sold it to Tricep. And when the consultant came in, he kind of like confided to me what we were doing wrong. And I'm going to tell this story because I think it's something that I could learn from. Is we used to coat the polysiphone in a separate coater, and we do bubble tests to make sure it was perfect, and we measure the flux of the polysiphone. Then we'd store it for a few days. And then we would then run it, and sometimes it would be weeks, and then we would run it through our thin film composite coater. And we didn't do kiss over roll coating like other people did. We had like a sleuth where we kind of like dragged it over, and we had use Freon, and we kind of like touched the membrane. And so when the consultant saw this, he says, you know, one of the things I think you did wrong here is that when you formed your polysiphone membrane, you had a lot of I think it was DMF that we were using as a solvent, but that's great food for bacteria. And so when you roll the polysiphone up, you're breeding bacteria, and now you take this membrane and you try to create a thin film on top of this membrane where there's bugs growing, and you don't get, I mean, we could get 98% rejection, but we couldn't get the 99. I later went over to Air Liquide, and they were doing a thin film composite, and they had these quench tanks, and Charlie, you may remember them, but they had sight glasses where it was like all crudded up, and they said they could never get it clean. And then I took Lynn's technique of taking Clorox and raising the pH up to 11 and recirculating, and we cleaned it, and all of a sudden the rejection on their membranes went up. And so I mean, what I learned from Tricep and that consultant, I ended up applying to that. But we made a lot of mistakes, and our core was really the hollow fiber, and we should have stuck with it because the membrane was indestructible, and we should have really looked at ways to make that membrane work more efficiently. And we did that later on, but we were like about 20 years too late, especially for B9. Because B9, we at the end, back in, 99, we were making triple cartridges out of B9, putting PTB on it and making almost like 2% salt passage at 200 pounds, running at like 75 or 80% conversion. So we had a really good brackish membrane, and it was the original B9 membrane that we had back late 70s.
In 60s,
but we
yeah.
just didn't know how to take that fiber and use it as effectively as we could have.
Hey, I think you retrofitted the Sarasota plant with twins,
I
as I recall.
don't remember what we did there.
Yeah, well,
I think
not
that
the,
was
not,
10-inch.
yeah, that was a 10-inch in Sarasota.
was 10 inches.
Because that's what Dow had. Dow had a 10-inch
Yeah.
CA membrane,
Was it 10-inch?
and that was the
'Cause
10. That was
I
the first
visited there.
10-inch B9s.
I'm sure I saw some longer. Maybe you didn't. Maybe you had some test units down there,
I
perhaps.
think we did.
Oh, okay, Sarasota, we did, yes, I
Yeah,
take that back.
yeah.
Sarasota, yeah.
Yeah.
Sarasota, we did retrofit with twins. Also, they had a severe biological problem down there. And they were testing spirals. And I went down there and I did the hypochlorite cleaning on their system, and I mean, it was a tremendous recovery. The guy couldn't believe how well it recovered. And one of the operators, he had the instructions that I gave him and went through it with me. And he was going to go around Florida and clean all these plants. The only problem was the CA, or the spiral people said, you cannot use that technique on our membranes. So they couldn't use it on our membranes, but it worked very well on DuPont membranes.
Yeah, I visited that Sarasota plant in 1999, and it was still operating.
Oh, yeah.
I think they had the original permeaters. in
Yeah,
there.
yeah.
It was years and years.
Yeah, well, one of the problems I had at Sarasota, and I don't know if you remember this or not, but the engineers that designed that plant insisted on putting in aluminum bronze pumps rather than stainless steel. And, all Florida groundwater is full of hydrogen sulfide.
Mm-hmm.
And when some of the permeators were opened up, I understand they found copper sulfide granules in the bundle.
Mm-hmm.
And that started to decline the performance. So when
Yeah.
we took the pumps out, we actually found that the impellers were about 95% or 90% of the diameter they were supposed to be.
We learned a lot. I can remember when I first came to Permacept, our original 4-inch B10 permeator had aluminum segmented rings. And in my desk, I kept the corroded aluminum ring to remind me not to use aluminum.
Not to use
in
aluminum,
water.
right? Yeah.
Let me just go back a couple of steps. When we talked about DuPont getting into the spiral business, DuPont actually bought a small spiral manufacturer in San Diego. I can't remember the name of the company, but
We
Chick
bought the
Osgood went out there, and
membrane.
Dave Stallhut went out there, and so we were making CA membranes, and then also we could use that plant to make our B-15s
You
and
bought
so forth.
the old Ajax
Ajax, that's it.
company,
what it
Yes,
was,
yeah.
Ajax.
Yeah, I remember that.
Yes.
Yeah, because they were big CA manufacturers
Mhm.
at one time.
But that was our attempt to get into the business, at least, buy a manufacturer, learn how to make the membranes. Or the
As we
systems.
come to
Don
the
Bray was the owner of the company.
Yeah. As we come to the conclusion of this interview, the question that everybody asks is that DuPont, having spent a lot of time and years and money achieving a position which at one time was dominant in the industry, decides to go away. Why was that decision made, do you know?
Well, I think we just told you they wanted to sell the nylon business in Waynesboro.
Well, I think it's also economics. DuPont gets concerned about the businesses making money. Permacept business was a $10 or $20 million business. I mean, that's like a grain of sand on the beach. We were nothing to DuPont. It wasn't worth the headache. You know, go away. In the early 60s and 70s, and especially the late 70s, DuPont looked at Permacept as like a crown jewel. We were going to really be something. And we had tremendous management at that time. Bob Keller was the business manager, and he was really outstanding guy. We had guys like Jack Sally in marketing. And then Bob Keller had to retire. He reached a certain age. He was forced to retire. Jack was promoted someplace else. Another guy came in, and we really lacked the leadership that these guys gave us. And Permacept was a unique business. It wasn't a typical DuPont business. It was like a little entrepreneurial business. And I remember we used to have meetings. We'd have a project would come up, and we would be called into the a conference room. The marketing people would be there, the manufacturing people would be there, the technical people would be there. And we'd be there, how can we win this project? We have to win this project. We can't keep cutting costs. What can we do? Technical people, what can you do to push the limits of the technology as far as what's acceptable, what you can do to, how far you can push salt passage, how far you can extend the life of the membrane, how far you can push conversion and things like that. So we were constantly trying to improve things like how far could we go with scaling. We used a Stiffen-Davis index for calcium carbonate control versus, say, the Langolier index, which was for brackish water. That allowed us to operate at higher pH, use less pH, or less acid in the plants. So that would save operating cost for the customer. So we would do things like that to try to cut our cost. And how can manufacturing, what can you do to boost the flow rate of the permeators up? How can you get a little extra fiber in or a little more productivity out of the units? How can you improve salt passage? Things like that. And all together like that, we'd sit there and go through these meetings, and we would come up with a project and cut the cost and win projects. That management in the early 80s unfortunately left. It was when Bob retired, it's like a new guy came in, and then other managers came in, and they just didn't have that same entrepreneurial skills, and things just kind of slowly disintegrated.
Yeah, they were used to running business where you sold
hopper cars,
plastic cubes and things like that.
Sell tank cars,
you know, and
stuff
they
like
didn't
that.
understand about negotiating with countries and large plants and
I mean,
long-term guarantees.
Jack Sally would come in, and he'd have one of these, Arab outfits on. He was an amazing guy. He was a real salesman.
I think one thing that happened is that once we got into the spiral wound, it tended to dilute our efforts.
Yeah.
And instead of remaining focused on our original product, it diluted the efforts, and yet we didn't have the technical support for all of everything. So obviously that was not a very good thing.
I agree.
One thing that you guys put together, which lives on, is the Permacept's technical manual. I have an original copy, I think, and I have a revised copy. I also still have the software on a 3.5-inch disc.
Floppy disk, yeah.
Yeah, and
Well, Lynn and I spent a lot of time.
that was a great manual. Nobody.
Irv Mock was the guy that was responsible for putting that together. He came into Permacept, and he would talk to Lynn, and he would talk to me, and he would talk to other guys, and he realized that, we have all this information, but it's just not put together. So he told us we're going to come up with this, the Permacept engineering manual, and I was the first person. I was in charge of putting together Section 4 on computer projections. So it was brutal. We spent several months going over every, little word, every
Line.
man. And there were like 15 people in a room, in this conference room, and it was just brutal. And after a while, we were down to 12 people. And after a while, we were down to 4 or 5 people. And after a while, it was Lynn and me and Irv. And it was an effort to go through it, but it was really well worth it.
I can tell you, none of the other membrane manufacturers have ever produced anything like that. That's comprehensive. And I still use it today. It's got
There's a
good
lot of good information in there.
barium sulfate, strontium sulfate solubility curves. And it was excellent. I want to thank you all for coming. It's been a great pleasure to meet you. And as Doug told you, you will be receiving a copy of this interview. And I hope when you see yourselves, you won't be too disappointed. Thanks very much.
Thank you.